All right, chapter 15, benzene and aromaticity. Okay. Benzene is a known carcinogen. We're going to see shortly that the structure is that of a flat planar molecule. And so, for instance, it very easily intercalates between DNA, and that can cause mutations and lead to cancer. A compound very closely related to this toluene has no such effects. Now, what's the difference? The difference is simply this methyl group. And of course, you know that in benzene, the carbon atoms that I have depicted are all sp2. But for toluene, we have this methyl group, and of course it is sp3, and therefore tetrahedral. Being tetrahedral, it is not flat. And so toluene, anybody ever experienced the odor of paint thinner? Most common paint thinner is toluene. So this seemingly very small difference has a huge impact on physical and chemical and biological properties of compounds. And that's why it's so important to understand the three-dimensional structure of these compounds. Because if you just looked at it and said, well, that's benzene and that's benzene, they must be the same, they must be identical, that would be what we call an overgeneralization. And one of the things that I want you to learn and take away from this class is to not overgeneralize. So these are important differences. One of the other big important differences, for instance, we learned in the last chapter that if we take cyclohexadiene, we can treat it with Br2, and of course it reacts and it produces a couple of different products. I'll just depict one. The bromine adds to the double bond, making this dibromide. But if I do the same thing with benzene, nothing happens. There's no reaction. So this tells us right away there's something different about bromine. About benzene in its reaction with bromine. So of course, we eventually do get reactivity of benzene with bromine. We get it to react by adding a catalyst, FeBr3. And when we add FeBr3, we actually do not get the expected addition product like we saw with cyclohexadiene. What we observe is in fact a substitution product. And because we get substitution, when we have a catalyst and we get the reaction to occur, this tells us that there's something special about benzene again, because you see the core structure came back. And that means there's some special stability about this versus cyclohexadiene. And so if we look, for instance, at, let me make sure I got my figure number correct here, 15.2, we see the thermodynamics of reduction for these compounds. So what we're going to do is we're going to compare the reduction of cyclohexene to cyclohexane. And according to your textbook, this reduction releases about 118 kilojoules per mole. If we go to cyclohexadiene, there's almost twice, with a release of 230 kilojoules per mole. That would then predict that benzene should release about 356 kilojoules per mole. But when we go and do the experiment, this is why experiment and real data is so important. When we do the actual experiment, we see that benzene actually only releases 206 kilojoules per mole. So there's a difference here of about 150 kilojoules per mole. And this significant difference in energy is what we call the aromatic stabilization energy of benzene. That is, when we have all three of these double bonds in benzene aligned in a double, single, double, single, double, single pattern, we get a very special stability that is referred to as aromaticity. Come back over here. And now we're going to, in the rest of this chapter, take a look at trying to understand where this comes from, how it occurs, and how we can then make use of it.